In the infinite hush between galaxies, where darkness is not empty but alive with potential, the universe whispers its deepest secret, not in light, but in fleeting phantoms that blink in and out of existence before time can notice. They leave no trail, cast no shadow, yet their influence stretches across cosmic distances, propping up reality like invisible threads in an unfathomable tapestry. These are virtual particles ghosts, birthed from nothingness, permitted only by the strange mercy of quantum uncertainty. They do not exist, and yet everything depends on them. This is the story of what isn't, but must be. In a universe governed by silence and symmetry, where stars are born in fire and galaxies spiral in slow celestial dance, there exists a deeper rhythm, an unseen current beneath the surface of reality. It does not shine, it does not collide, it cannot be held, nor seen, nor touched, and yet it holds everything together. This is the story of something that should not exist, something that flickers at the edge of measurement, too brief to catch, too essential to ignore. A phantom born not in cloud chambers or particle accelerators, but in the quiet desperation of equations scrawled on chalkboards in dimly lit offices. A creature of mathematics, first of matter, never. The virtual particle, the ghost in the machine of modern physics. It begins in 1935 in Kyoto, Japan, where a young theoretical physicist named Hideki Yukawa walked through autumnal streets lined with ginkgo trees, his mind adrift in the subatomic world. At the time, the atom was still a mystery wrapped in paradox. Protons huddled tightly in the nucleus, packed side by side, despite their identical positive charges, repelling one another with ferocious electromagnetic force. And yet, they did not fly apart. Something stronger held them together. Something invisible. Something unknown. Yukawa dared to ask, what if forces are not magic? What if they are carried? He imagined a messenger, a particle darting between protons and neutrons, binding them like unseen threads woven through space itself. But this particle could not be ordinary. It had to appear only when needed, vanish before detection, live for less than a trillionth of a second, too short a life to ever be observed directly, too vital to dismiss as fiction. He called it the meson, a middleweight between electron and proton, and predicted its mass based on the range of the nuclear force. His theory was elegant, audacious, but nature remained silent. No such particle appeared in cosmic rays or laboratory detectors. For nearly a decade, Yukawa's idea lingered in limbo, mathematically sound, experimentally absent. Then, in 1947, something strange fell from the sky, high above the Earth. In the upper atmosphere, cosmic rays collided with nitrogen nuclei, sparking showers of exotic particles. Among them, British physicists Cecil Powell and Giuseppe Occhialini discovered a new entity, a particle with almost exactly the mass Yukawa had predicted. They named it the Pimeson, or Pion. At last, the strong force seemed to have its carrier. But joy turned to confusion. When scientists tried to probe deeper, they found a dissonance. The pion interacted too weakly with nuclei to be Yukawa's true messenger. It was a mimic, an imposter. The real force-bearer remained hidden. Meanwhile, across the Atlantic, a different revolution was unfolding, one not of detection, but of calculation. quantum electrodynamics, or QED, was being forged in the crucible of post-war American physics. At Cornell, Harvard, and Tokyo, minds like Richard Feynman, Julian and Shinichiro Tominaga wrestled with the behavior of electrons and photons, how light and matter whisper to each other across empty space. Their equations were precise, predictive, breathtakingly accurate, but they were also haunted. Every time they calculated how an electron should behave, how it scatters light, how it orbits a nucleus, they encountered infinities, unholy numbers that stretched toward eternity, breaking the math. These were not errors. They were consequences of quantum fields interacting with themselves, looping back in recursive feedback. The electron, it seemed, was never truly alone. Even in isolation, it shimmered with activities, rounded by a cloud of fleeting influences. To fix this, theorists introduced a radical idea. Within the calculations, they allowed for particles that briefly popped into existence, electron-positron pairs only to vanish moments later, as if ashamed of their own presence. These were not real particles in the traditional sense. They violated energy conservation, existed outside time, defied observation. And yet, without them, the numbers failed. They called them virtual particles, not because they were fake, but because they lived in the interstitial spaces of quantum reality, between emission and absorption, between what is asterisk and what asterisk could be asterisk. The term was a compromise, a linguistic surrender to the absurdity of a universe where existence is not binary, but probabilistica, spectrum, stretching from definite matter to transient possibility. And then came 1947, not just the year of the peon's discovery, but the year reality blinked. At Columbia University, Willis Lamb and Robert Rutherford conducted an experiment so delicate it bordered on meditation. They measured the energy levels of hydrogen, the simplest atom, a single electron orbiting a proton. According to Dirac's equation, two specific states 2S and 2P should have identical energy. But Lamb found a tiny, persistent shift, a difference of just 1,000 megahertz less than a fraction of a percent, but enough to shatter perfection. This was the asterisk, Lamb shift, asterisk, a crack in the foundation of quantum theory. And through it poured a flood of implication. The shift could not be explained by classical electromagnetism, nor by Dirac's original formulation, but when Hans Bethe applied the new methods of QED, when he included the effects of virtual photons being emitted and reabsorbed by the electron, of the vacuum itself trembling with transient fluctuations, the number matched perfectly. The vacuum, once thought to be inert, passive, a mere stage for particles to perform upon, was revealed as an active participant in reality. It buzzed, it pulsed, it whispered to electrons, nudging their orbits, altering their energies. The virtual particle was no longer a mathematical trick. It was necessary. It was real in the only way that matters in quantum physics. It made correct predictions. But what, then, is a virtual particle? Not a thing. Not in the conventional sense. It has no trajectory. It cannot be detected. It does not leave a track in a bubble chamber. It violates the relativistic energy-momentum relation. MRCC. Real particles obey it. Virtual ones do not. They are off-shell, existing in a liminal state, permitted only by the uncertainty principle. Heisenberg's principle, often cited as you can't know position and momentum at once, has a lesser-known twin. Energy and time are similarly uncertain. For very short durations, energy can fluctuate, borrowed, spent, repaid, before the universe notices. This is the loophole through which virtual particles emerge. The vacuum is not empty. It is a seething foam of potential pairs of particles and antiparticles blinking into existence, annihilating, vanishing all within timescales of $10, $21 seconds or less. These are the quantum vacuum fluctuations, the static hum of spacetime itself. Feynman diagrams gave them form. In those deceptively simple sketches, lines meeting at vertices, wavy photons bridging electrons, virtual particles became visible as internal lines, connecting events like invisible threads. They were the intermediaries, the unseen handshakes between real particles, yet they remain paradoxical. Are they real, or just tools? Some physicists argue they are merely terms in a perturbation series and infinite. Others point to measurable effects, the Casimir effect, where two uncharged metal plates placed nanometers apart in a vacuum experience an attractive force. Why? Because the space between them restricts the wavelengths of virtual photons that can form, creating a pressure imbalance. The result? The plates are pushed together by the vacuum itself. Or consider Hawking radiation. Near a black hole's event horizon, virtual particle-antiparticle pairs form. One falls in, the other escapes. The black hole appears to radiate. Energy is lost. Over eons, it evaporates. All from a process rooted in virtual fluctuations. These are not abstract curiosities. They are predictions confirmed by logic, consistency, and indirect evidence. The virtual particle, though never observed directly, shapes the fate of stars and atoms alike. And here lies the philosophical vertigo. We speak of particles as asterisk things, asterisk solid, localized, independent, but quantum field theory tells us otherwise. Particles are excitations of underlying fields, ripples in a cosmic medium. The electron field, the photon field, the Higgs field. These fields permeate all of spacetime. What we call a particle is merely a knot of energy in that field, stabilized, detectable. Virtual particles are ripples too, but unstable, transient, constrained by the rules of interaction. They are the background noise of the fields, the static between stations. Yet, without that noise, the signal would be incomprehensible. Paul Dirac had glimpsed this decades earlier. In 1928, his relativistic equation for the electron demanded symmetry between positive and negative energy states. To prevent electrons from collapsing into negative energy, he proposed a Cn infinite ocean of filled negative energy states, invisible, uniform. When disturbed, a bubble in this sea would appear as a positively charged counterpart, the positron, discovered in 1932 by Carl Anderson. The Dirac sea was later reinterpreted in quantum field theory as the vacuum state, the ground level from which all excitations arise. But the lesson endured. Emptiness is an illusion. The void is fertile. By the 1950s, the Standard Model began to coalesce. Forces were no longer actions at a distance, but exchanges of gauge bosons for electromagnetism, W and Z bosons for the weak force, gluons for the strong. Each force had its messenger, and each messenger in interactions could be virtual. When two electrons repel, they exchange a virtual photon, not a beam of light, but a temporary disturbance in the electromagnetic field, carrying momentum, enforcing the law of repulsion. The photon lives only as long as the uncertainty principle allows long enough to deliver its message, short enough to evade detection. Similarly, inside the nucleus, protons and neutrons exchange virtual pions, or, more accurately, virtual gluons, and quark-antiquark pairs, mediating the residual strong force. These exchanges create the binding energy that overcomes electromagnetic repulsion. Even gravity, though not yet quantized, may operate through virtual gravitons in some future theory ghosts of space-time curvature, flitting between masses. But the deeper one looks, the more the distinction between real and virtual blurs. A real photon, say, one emitted by a star, can travel billions of years across the cosmos. It is on shell, satisfying energy-momentum relations. But during its journey, it may briefly fluctuate into a virtual electron-positron pair, then back into a photon. This is vacuum polarization, a correction in QED that affects how light propagates through space. Is the photon still real, or is it, even in flight, partially ghost? And what of the Higgs boson? Discovered in 2012 at CERN, it was hailed as the capstone of the Standard Model, but even it interacts through virtual loops. The mass of the W and Z bosons, crucial to the weak force, depends on virtual top quarks influencing the Higgs field particles, so heavy they've never been directly involved in the interaction. Yet their ghostly presence alters the fabric of reality. This is the universe's subtle choreography, the visible shaped by the invisible, the actual molded by the possible. And still, questions linger in the silence. Are virtual particles really popping in and out of existence? Or are they merely mathematical artifacts, useful fictions that encode the complexity of quantum fields? Some interpretations, like the transactional interpretation, suggest virtual particles are echoes of future events, waves sent backward in time to complete a handshake across space-time. Others, like the many worlds interpretation, dissolve the paradox entirely. Every fluctuation branches reality, but we only perceive the average. Loop, quantum gravity, and string theory offer alternatives. Perhaps space-time itself is discrete, and the vacuum foam is literal, a frothing lattice at the Planck scale, $10, $35 meters. Their virtual particles might be vibrations of strings or twists in spin networks, real but beyond measurement. But until a unified theory emerges, the virtual particle remains both cornerstone and enigma. It challenges our intuition about existence. Must something be observable to be real? Or is influence enough? A shadow proves the presence of light. A ripple implies water. The Lamb shift, the Casimir effect, the precision of QEDs are shadows cast by virtual particles. We see not the thing itself, but the shape of its absence. In this way, the virtual particle becomes a metaphor for all that lies beyond perception: dark matter, dark energy, the quantum origins of space-time. The universe speaks in hints, in residuals, in deviations from expectation. And perhaps that is the deepest truth. Reality is not only what is measured, it is also what must be assumed for the measurements to make sense. So we return to Yukawan with answers, but with reverence. He proposed a force-carrying particle before any instrument could detect it. He trusted the math. He believed in the unseen. Today, we stand further into the unseen than he could have dreamed. Not just particles, but entire processes that exist only in the space between equations yet hold atoms together, guide light, shape the vacuum. That the virtual particle is not a mistake. It is a revelation that the universe runs on ghosts, that the solid world is built on borrowed energy and fleeting possibilities, that beneath the silence of empty space, there is a symphony inaudible, invisible, eternal, played by instruments that exist only long enough to strike a note. And when we look into the heart of matter, we are not seeing substance, we are seeing the echo of nothingness, dancing. There is a silence deeper than the void between stars, a stillness not of absence, but of tension and emptiness that breathes, pulses, pushes. In 1997, in a laboratory at the University of Washington, physicist Steve Lamero sealed 2 polished metal plates into a vacuum chamber. They were smooth, inert, uncharged, separated by less than a micron. A gap so narrow that light itself struggled to pass through. There were no magnets, no electric fields, no visible force acting upon them, and yet, over time, they began to move, slowly, inexorably, toward one another. It was not gravity. The plates were too light, too far apart for such a weak force to matter. It was not electromagnetism. They carried no charge. What pulled them together was something far stranger, something that should not exist. It was the pressure of nothing, or rather, the imbalance of everything that flickers within nothing. This was the Casimir effect, first predicted in 1948 by Dutch physicist Hendrik Casimir, but now, for the first time, measured with precision. And in that quiet drift of metal, a truth emerged as unsettling as it was undeniable. Empty space is not empty. It has weight. It has texture. It exerts force, and its power comes from particles that are not supposed to be there. Long before Lamaro's experiment, the idea had already taken root in the minds of theorists, a whisper in the equations of quantum field theory. If the vacuum is truly the lowest energy state, why does it behave like a storm? Why do calculations demand the presence of fleeting particles, blinking in and out of existence, violating every classical law of permanence? These are the virtual particles entities born of Heisenberg's uncertainty principle, which allows energy to be borrowed from the void, provided it is repaid quickly enough, for a duration shorter than $10, 21 seconds. A pair of particles and electron and its antimatter twin, the positron, can erupt from the vacuum, dance for an instant, then vanish back into non-existence. No detector can capture them. No instrument can track their path. They leave no direct trace, and yet their influence echoes across reality. They are not real in the way a photon streaming from a distant quasar is real. They do not travel through space with measurable momentum. They are off-shell, existing outside the relativistic constraints that govern ordinary matter. But they are necessary, mathematically, physically, cosmically, and the Casimir effect proves it. Between those 2 plates, only certain wavelengths of virtual photons can fit those whose half wavelength divides evenly into the gap. Outside, however, all wavelengths are permitted. The result is an asymmetry. More virtual particles press from the outside than from the inside. Like ocean waves pounding against a seawall, the external vacuum fluctuations push the plates together. It is not magic, it is measurement. The force is tiny in the order of billionths of a Newton, but it is real, calculable, repeatable. And in that calculation lies a philosophical earthquake for centuries. The vacuum was synonymous with emptiness, the blank slate upon which physics painted its laws. Newton imagined space as an absolute stage, passive and unchanging. Even Einstein, who wove space and time into a dynamic fabric, treated the vacuum as a smooth continuum, warped by mass and energy, but fundamentally inert. But quantum field theory tells a different story. Every point in space is a nexus of fluctuating fields: the electromagnetic field, the electron field, the gluon field, all seething with potential. The vacuum is not still. It is the most active place in the universe, a frothing sea of transient excitations, where particle and particle pairs blink into being and out again, where photons flicker like fireflies in a midnight storm. This is the quantum vacuuma living void. And if the void is alive, then nothing is truly solid. Consider the atom. 90-9-0.9-99% of its volume is empty space. The nucleus, a speck at the center, surrounded by electrons orbiting at vast distances relative to their size. If a hydrogen atom were scaled to the size of a cathedral, the proton would be a grain of sand on the alterand, the electron, a mote of dust swirling near the rafters. Yet the atom holds its shape. Matter feels solid. A table resists your hand. A planet stays whole. Why? Because that empty space is not empty. It is filled with virtual particles mediating forces. The electromagnetic repulsion between your hand and the table is carried by virtual photons, countless ghostly exchanges, preventing atoms from overlapping. The strength of materials, the rigidity of steel, the transparency of glasol emerge not from substance, but from interaction. Even mass itself may be an illusion of exchange. The Higgs field permeates the cosmos, and as particles move through it, they interact via virtual Higgs bosons, acquiring inertia. An electron is not heavy because it contains internal weight. It is heavy because it dances with the vacuum, dragging against the field like a figure wading through fog, and time. Is it immune? Perhaps not in extreme environments near black holes. In the first instance of the Big Bang, the distinction between virtual and real begins to dissolve. Stephen Hawking showed that at the edge of a black hole's event horizon, virtual particle pairs can be torn apart. One falls in, the other escapes as radiation. The black hole slowly evaporates, not from within, but from the vacuum just outside. Here, the temporary becomes permanent. The virtual becomes real. Energy is conserved only globally. The infalling particle carries negative energy, reducing the black hole's mass, while the outgoing one carries positive energy into the universe. The vacuum lends its ghosts to cosmic transformation. And if virtual particles can escape a black hole, what else might they do? Some theories suggest that during cosmic inflation, the exponential expansion of the early universe quantum fluctuations were stretched across space-time, seeding the formation of galaxies. Tiny ripples in the vacuum, frozen into structure by rapid expansion, became the scaffolding of the cosmos. Data from the Planck satellite confirms this. The distribution of galaxy clusters across the sky mirrors the statistical patterns of quantum noise. The universe, in its grandest structures, bears the fingerprint of the ephemeral, quite literally made from amplified randomness, and yet the paradox deepens if virtual particles violate energy conservation. Even briefly, does that mean the first law of thermodynamics is not absolute, not violated, refined? Heisenberg's energy-time uncertainty principle allows for temporary imbalances. $delta E, delta T, Jek HBr, $2. The shorter the time, the greater the energy fluctuation permitted. On timescales of $10, $23 seconds, enough energy exists to create a W bosonor, even hypothetically, a microscopic black hole. These fluctuations are not exceptions to physics. They are part of it, in fact. Without them, the universe would be static, lifeless, predictably wrong. The Lamb shift, discovered in 1947, revealed that the electron in a hydrogen atom experiences a slight jitter due to its interaction with virtual photons. This tiny correction, barely detectable, could not be explained by classical theory. Only when quantum electrodynamics included vacuum fluctuations did the numbers align. Reality depends on phantoms, and the deeper we look, the more pervasive they become. In 2015, the LIGO collaboration detected gravitational waves from two merging black holes. The signal matched Einstein's predictions with astonishing precision, but theoretical work suggests that quantum vacuum fluctuations may introduce subtle noise into such measurements, ripples in space-time itself, generated not by distant collisions, but by the froth of virtual gravitons. We may soon reach a limit, not of technology, but of space-time, a fundamental haze beneath all observation, set by the Planck scale, where the vacuum churns with fluctuations so violent they blur the very notion of location. At $1.60 times 10 minus $35 meters, space may cease to be smooth. It may become granular, foamy, turbulent like water seen at the molecular level. Some models predict that high-energy gamma rays from distant blazars should arrive at slightly different times, depending on wavelength, if space-time is quantized. Observations from the Fermi Gamma Ray Space Telescope have placed tight constraints on such effects so far. Space-time appears smooth, but the search continues. Because if the vacuum has structure, then reality is built on instability. And if virtual particles define that structure, then existence itself rides on borrowed time. This raises a haunting question. Are we merely averaging over chaos? In quantum mechanics, what we observe is not individual events, but probabilities. We do not see each virtual pair appearing and vanishing. We see their net effect, the Casimir force, the Lamb shift, the mass of particles. Reality, as we experience it, may be a smoothed-over version of a frenzied underlying process, like watching the surface of the ocean from high above, reflective while beneath storms rage in the depths. Some interpretations of quantum mechanics take this further. The transactional interpretation, proposed by John Cramer, suggests that virtual particles are echoes of future events offerings sent backward in time to complete interactions. A photon emitted by a star doesn't just travel forward. It sends a handshake wave backward through time, meeting its absorption event. Virtual particles are the intermediaries in this temporal negotiation. It sounds like science fiction, and yet it produces the same predictions as standard QED. Others, like the many worlds interpretation, avoid the issue entirely. Every fluctuation branches reality. In one universe, a virtual pair appears. In another, it does not. We inhabit the average, the Descartes, sum of infinite possibilities. But none of these answers erase the mystery, because the deeper implication of virtual particles is not just that they exist, that reality is relational. An electron is not a discrete object. It is a node in a network of interactions, surrounded by a cloud of virtual photons, constantly emitting and reabsorbing. Its properties: mass charge, magnetic momentar shaped by the vacuum around it. Remove the virtual particles, and the electron changes. It may not even make sense. In this view, particles do not have properties. They are their relationships, and the vacuum is not a backdrop. It is a participant, which leads to the most unsettling possibility of all. Perhaps the universe began not with a bang, but with a fluctuation. In some cosmological models, our entire cosmos could be a rare, stabilized vacuum fluctuation in improbably long-lived bubble in a greater meta-universe. Alan Guth's theory of inflation suggests that a false vacuum state, unstable configuration, could drive exponential expansion, cooling into the universe we see. And if so, then everything, the Milky Way, Earth, consciousness rose from a quantum hiccup in an eternal void, a phantom that refused to disappear. So when we say the universe is made of particles, we must ask, which ones? The ones we see, or the ones we never can? The electron in your hand, the light in your eyes, the air in your lungs, all are sustained by exchanges with entities that exist only in the cracks of causality, forces mediated by messengers that live too briefly to be real. We walk through life touching surfaces that are mostly nothing, held together by processes that defy time, powered by energy drawn from emptiness. And still, the question lingers: if reality runs on illusions, is it less true, or is it more profound? Perhaps solidity was always a dream. Perhaps permanence is the myth. The ancient Greeks spoke of physis nature as becoming, not being. Eastern philosophies describe the world as Maya, illusion veiling deeper unity. Now, modern physics whispers the same. The universe is not a machine of gears and levers. It is a conversation between fields, between particles, between now and not yet. And at the heart of that dialogue, in the silent space between measurement and meaning, stand the virtual particle sin, indispensable ghosts in the code of existence, whispering to us, not in words, but in force, in shift, in drift, in the slow, an inevitable pull of two plates in a vacuum, reminding us that even nothing has weight. In the deep tunnels beneath the French-Swiss border, where superconducting magnets hum at temperatures colder than interstellar space, protons race through a vacuum ring 27 kilometers in circumference, accelerated to 99.99999% of the speed of light before colliding in bursts hotter than the heart of any star at CERN's Large Hadron Collider. These collisions are not merely explosions. They are interrogations. Each impact is a question hurled at the fabric of reality. What are you made of? How do forces begin? What unseen hands guide the dance of matter? And from the debris showering through layers of silicon trackers, calorimeters, and muon detectors comes an answer written in code. A language of energy, momentum, charge. A script so precise, so consistent, that it points not to what is seen, but to what is missing. Because within every collision, something invisible shapes the outcome. Not a hidden particle buried in data, not a new force waiting for discovery, but a constant, silent presence, trillions of ephemeral actors flickering in and out of existence faster than time can register, orchestrating the behavior of everything real. They are the virtual particles, the unseen architects of the Standard Model by the 1970s. Quantum electrodynamics (QED) had achieved a precision so staggering it defied belief. Predictions of the electron's magnetic moment matched experiment 212 decimal places, 1 part in a trillion. No theory in human history had ever aligned so perfectly with observation, and yet every digit of that accuracy relied on terms representing particles that never existed. Feynman diagrams, those elegant sketches of lines and vertices, were no longer just pedagogical tools. They were computational engines. Each internal line, each loop, represented a virtual exchange, a photon darting between electrons, a gluon briefly binding quarks, a W boson mediating the decay of a neutron into a proton. These were not hypotheticals. They were mathematical necessities. Remove them, and the numbers collapsed. The universe, as measured, would no longer make sense at the LHC. This reliance becomes tangible. When two protons collide, they do not simply break apart like billiard balls. They interact through fields, quantum fields whose excitations manifest as particles. But the path from initial state to final debris is paved with virtual intermediaries. A Higgs boson emerges not from direct fusion, but from loops of virtual top quarks influencing the interaction. A rare decay of a B meson deviates slightly from expectation, not because of new physics, but because virtual Z bosons and photons subtly alter the amplitude. These deviations, predicted decades earlier, appear now in petabytes of data, confirming that even in the most violent events in the laboratory universe, the ghostly undercurrent of virtual processes governs the outcome. It is not exaggeration to say that without virtual particles, the Standard Model would cease to function. They are woven into its syntax, its grammar, its truth, and their influence extends far beyond the detector cosmologists. Gazing at the oldest light in the universe, the cosmic microwave background, CMBC, ripples etched across the sky. These temperature fluctuations, imprinted when the universe was just 380,000 years old, are the blueprints of all future structure, galaxies, clusters, voids. But where did those ripples come from? Not from pre-existing matter, not from turbulence or collapse. According to inflationary theory, they arose from quantum fluctuations, microscopic jitters in the inflaton field, stretched to cosmic scales by exponential expansion during the first $10, $32 seconds after the Big Bang. And what are quantum fluctuations, if not the birth cries of virtual particles? In the primordial vacuum, Pairs of virtual particles flickered in and out of existence, just as they do today. But during inflation, space-time expanded faster than these fluctuations could annihilate. They were frozen, promoted from transient ripples to permanent density. Variations. When the universe cooled and matter decoupled from radiation, these variations became visible in the CMB. The Planck satellite mapped them in exquisite detail, revealing a statistical pattern Gaussian scale adiabatic that matches the predictions of quantum vacuum fluctuations amplified by inflation. In other words, the largest structures in the cosmos, the filaments of galaxy clusters, spanning billions of light years, grew from seeds planted by virtual processes in a realm smaller than a proton. We are stardust, yes, but we are also vacuum dust, descendants of fluctuations that lasted less than a trillionth of a second. And still, the paradox remains. None of this has ever been seen directly. No instrument records the birth of a virtual electron-positron pair. No camera captures the fleeting exchange of a gluon between quarks. Their existence is inferred through calculation, through consequence, through the silent pressure they exert on measurable reality. Yet their effects are everywhere. Gravitational lensing. The bending of light around massive objects is described by general relativity, but quantum corrections mediated by virtual gravitons in theoretical extensions of gravity could introduce subtle deviations at extreme energies. While not yet observed, such effects may one day reveal themselves in the timing of pulsars or the polarization of the CMB. Even time itself may bear their mark. In 1974, Stephen Hawking published a paper that would unravel the classical picture of black holes. He showed that they are not entirely black, applying quantum field theory near the event horizon. Hawking realized that virtual particle pairs constantly forming in the vacuum could be torn apart by the black hole's immense gravity. One partner falls in, carrying negative energy. The other escapes to infinity, appearing as real radiation. This is Hawking radiation, a slow thermal glow predicted to emanate from all black holes. And in this process, the unreal becomes real. The escaping particle gains energy not from the black hole's interior, but from the gravitational field at its edge. As negative energy particles fall in, the black hole loses mass. Over eons, it evaporates. For a stellar mass black hole, this process takes 1,067 years, far longer than the current age of the universe. But the principle stands. Virtual processes can extract energy from space-time curvature, converting possibility into permanence. No direct detection of Hawking radiation exists, but analog experiments have offered tantalizing hints. In 2016, Jeff Steinhauer created an artificial event horizon in a Bose-Einstein condensate, observing phonon pairs emerging with the thermal spectrum predicted by Hawking. The correlation between inside and outside modes mirrored the entanglement expected from virtual pair separation. It was not a black hole, but it was a mirror, and in that reflection, the boundary between virtual and real blurred beyond recognition. Because if a virtual fluctuation can become real under the right conditions, then perhaps realness is not a fixed property, but a phase, like water freezing into ice. A quantum fluctuation, given the right environment, can crystallize into matter. This idea echoes through speculative cosmology. Some theories propose that the Big Bang itself was not a singularity, but a quantum tunneling event from nothing, or from a prior vacuum state triggered by a rare, large-scale fluctuation. Alexander Vilenkin's tunneling from nothing model suggests the universe began as a microscopic bubble, nucleated by quantum uncertainty, then inflated into the cosmos we inhabit. If true, then everything space, time, stars, life emerged from a virtual fluctuation that refused to vanish. And if so, then the distinction between something and nothing may be thinner than we dare imagine. Still, skepticism lingers. Are virtual particles truly physical, or are they merely terms in a perturbative expansion and infinite series used to approximate complex interactions like harmonics in a musical chord? Some physicists, like Robert Lachlan, argue that what we call particles may be emergent phenomena quasi-particles in a deeper medium. Much like sound waves in air are not fundamental, but collective excitations. In this view, virtual particles are not entities, but descriptors of field correlations. Others, like Chris Fields, suggest that space-time itself may emerge from quantum information networks, where virtual exchanges represent entanglement links, not material events. Yet even in these interpretations, the effect remains unchanged. The Lamb shift occurs. The Casimir plates move. The LHC measures deviations, matching loop corrections. The CMB bears the imprint of quantum noise. Whatever virtual particles are, they shape reality. And perhaps that is the only definition of existence that matters. Because in science, being real does not require visibility. It requires consistency, influence, necessity. Neutrinos were once undetectable. Dark matter remains invisible. Gravitational waves eluded us for a century. Yet all were accepted as real long before direct observation, because the universe behaved as if they were there. So too with virtual particles. They are the scaffolding beneath the visible world, the hidden choreography behind every force, every decay, every spark of light. And in their silence, they whisper a deeper truth. Reality is not built from solid things. It is built from relationships, from exchanges, from moments so brief they defy time, yet so essential they define it at CERN. When the beams collide, sensors record not particles but energy deposits. Algorithms reconstruct trajectories. Physicists interpret patterns, and somewhere in the chain from proton to pixel there is a gap. A space where no measurement reaches, where equations speak of ghosts. That gap is where the universe breathes, where the possible dances with the actual dot, where for a fraction of a nanosecond, nothing becomes everything. And so, as the LHC prepares for higher luminosity, as future colliders plan to probe the tera-electron-volt frontier, the search continues, not just for new particles, but for deviations from the predictions that include virtual loops. Any mismatch could signal new physics, extra dimensions, supersymmetry, or even a breakdown of locality. The idea that interactions happen at points in space, but even if no anomaly appears, the lesson endures. We live in a universe sculpted by phantoms, governed by mathematics, held together by forces carried on the backs of beings that exist only long enough to deliver their message, then vanish. Like footprints in snowfall, they are never seen, and yet, without them, nothing would stand. not an atom, not a star, not a thought. The virtual particle is not a footnote in the story of matter. It is the ink. There is a silence older than time, a stillness that predates stars, galaxies, even the concept of light. It is not empty. It does not sleep. It waits. This is the vacuum knot, as Newton imagined it, a passive stage for matter to perform upon, nor, as Einstein saw it, a geometric fabric warped by MASPA, as quantum field theory reveals, a living, breathing entity, seething with potential, a cosmic womb where particles flicker into being and vanish like thoughts in a dream. And from this restless nothingness, everything has emerged. By the late 20th century, physicists had grown accustomed to the idea that virtual particles arise from the vacuum-fleeting manifestations of quantum fields, permitted by Heisenberg's uncertainty principle. But as calculations deepened, a question arose, quiet at first, then deafening. What is the vacuum itself? If virtual particles are real enough to shift atomic energy levels, push metal plates together, and seed galaxies across the cosmos, then the vacuum cannot be mere absence. It must have structure, energy, weight. And so they tried to calculate it using quantum field theory. Physicists summed the zero-point energies of all possible fluctuations, the infinite spectrum of virtual photons, electrons, quarks, and more across every point in space. Each mode of the electromagnetic field, even in its ground state, carries a tiny energy, $frac 12 HBr OMEG $. Multiply that by the infinite number of possible frequencies, and the total vacuum energy diverges. Theorists imposed a cutoff at the Planck scale, the smallest meaningful length, $10, $35 meters, where quantum gravity should take over. The result? A predicted vacuum energy density of approximately $10, $112 erg per cubic centimeter. But observations told a different story. In 1998, two independent teams studying distant type Ia supernova discovered that the expansion of the universe is accelerating. Something was pushing space-time apart. They called it dark energy. Its measured energy density, $10, $8 erg cm. That is a discrepancy of 120 orders of magnitude, one of the worst mismatches in scientific history. This is the cosmological constant problem, the single greatest unsolved puzzle in theoretical physics. Not merely an error in calculation, but a chasm between expectation and reality, so vast it suggests a flaw in our understanding of existence itself. Why is the vacuum so calm? Why doesn't its immense theoretical energy curve space-time into a knot smaller than an atom? Either nearly all contributions cancel out with impossible precision down to 1 part in $10 $120 roar. Our entire picture of virtual particles and vacuum fluctuations is fundamentally incomplete. Some propose symmetry, supersymmetry, a theoretical framework linking fermions and bosons, could allow positive and negative vacuum energies to cancel exactly if it were unbroken. But if supersymmetry exists, it is hidden at energies beyond current detection. In our universe, it is broken. The cancellation is imperfect. Others suggest anthropic reasoning. In a multiverse of countless vacua, only those with near-zero dark energy can support galaxies, stars, and observers. We exist because the vacuum is finite, not by design, but by selection. But such answers feel less like resolution and more like surrender, retreat into metaphysics when mathematics fails, and yet the vacuum remains active. Observably so, because if the vacuum holds energy, it shapes the fate of the cosmos. Dark energy, whatever it is, dominates the universe's evolution. It stretches space-time, driving galaxies apart. In hundreds of billions of years, all but the nearest clusters will vanish beyond the cosmic horizon, leaving future civilizations staring into a black, empty sky universe ever existed beyond their island galaxy. And all of this may stem from the same quantum foam that gives rise to virtual particles. But there is a darker possibility. What if the vacuum is not stable? In quantum field theory, systems can exist in false vacuum-metastable states that appear stable but are not the lowest possible energy configuration. Like a ball resting in a shallow valley, separated by a hill from a deeper one, the universe could be poised on the edge of collapse. A sufficiently large fluctuation, virtual or otherwise, could tunnel through the barrier, triggering a phase transition. A bubble of true vacuum would nucleate, expanding outward at nearly the speed of light. Within it, the laws of physics would change. Particles might gain different masses. Forces could unify or dissolve. Atoms, molecules, life none could survive. This is false vacuum decay, a doomsday scenario, not of fire or ice, but of rewriting. Not destruction, but replacement. And it could begin at any moment, anywhere. No warning, no sign. Just a sphere of new physics, advancing silently, erasing everything in its path. Theoretical work suggests our Higgs field may reside in such a metastable state. Measurements of the Higgs and top quark masses, particularly from CERN, hint that the electroweak vacuum could be unstable on cosmological timescales. The probability of decay in any given year is infinitesimal, but over eternity, even the improbable becomes inevitable. We may live in a universe that is, quite literally, temporary. And if so, then the vacuum is not just a foundation, it is a threat. Yet within that danger lies another mystery. Perhaps we owe our existence to a prior collapse. Some cosmologists propose that our universe did not begin at the Big Bang, but emerged from a previous vacuum state, an eternal meta-universe, where quantum fluctuations spawn bubble universes endlessly. Ours may be one such bubble, born when a false vacuum decayed into a lower energy phase, releasing energy that became matter, radiation, space, and time. In this view, inflation was not the beginning, but a phase transition. The Big Bang was not creation, but consequence. And if virtual fluctuations can trigger such events, then the universe itself may be a stabilized ghost, a ripple in the void that refused to disappear. Alan Guth once mused, "The universe may be the ultimate free lunch, but if it arose from a quantum fluctuation, it was not free, it was borrowed. And one day the debt may come due." As these ideas stretch toward philosophy, the boundary between science and speculation thins. But experiments continue to probe the edge in laboratories. Quantum entanglement challenges the classical notion of locality. When two particles are entangled, measuring one instantly determines the state of the other even across light year. Einstein called it spooky action at a distance, rejecting its implication of faster than light influence. yet experiments confirm it. The Bell inequalities are violated. Reality is non-local now. Some theories suggest that entanglement may be mediated by virtual processes, by wormholes in spacetime, geometry E equals EPR conjecture, or by instantaneous exchanges through the vacuum's quantum foam. Could information flow through virtual channels outside of time? In 2022, experiments at Delft and Vienna demonstrated entanglements, swapping, and loophole-free Bell tests with increasing sophistication. Meanwhile, studies of vacuum polarization in strong electromagnetic fields, such as those generated by ultra-intense lasers, show anomalies consistent with nonlinear quantum electrodynamics, where virtual pairs affect the propagation of light in ways that mimic superluminal phase velocities. Not true, faster than light signaling, but hints that the vacuum distorts causality in subtle ways. And if virtual particles participate in entanglement, then they are not merely ephemeral disturbances, they are threads in a deeper network of connectivity. Perhaps the vacuum is not fragmented, but unified, a single quantum field, knotted into particles, stretched into space, vibrating with memory. This echoes the holographic principle proposed by Gerard T. Hooft and Leonard Susskind, which suggests that all information within a volume of space is encoded on its boundary. The three-dimensional universe may be a projection of a two-dimensional surface, like a cosmic mirage. In such a framework, virtual particles could be artifacts of encoding redundant data in the cosmic ledger, not physical entities, but necessary for consistency. Even time may emerge from entanglement. The Page-Wouters mechanism proposes that time is not fundamental, but arises from correlations between quantum systems. Without change, without interaction, without virtual exchanges, there is no now. So when we ask what the vacuum is, we may be asking the wrong question. It is not a thing. It is the condition of possibility, like silence before sound, like darkness before light. It is the substrate from which reality condenses. And if it dreams, perhaps it dreams us, because now, the final paradox emerges. If virtual particles mediate forces, shape galaxies, and may even carry information across space-time, then how can we call them unreal? They leave no tracks. They cannot be isolated. They violate energy conservation and flirt with causality. And yet, without them, the universe would unravel. Atoms would disintegrate. Light would not scatter. Black holes would not evaporate. The cosmos would lack structure. Their effects are measurable, their necessity undeniable. So perhaps the mistake was never in the theory, but in our language, we cling to words like real, existent, physical as if reality were binary. But quantum mechanics has taught us otherwise. The world is probabilistic, relational, contextual. A particle is not an object, it is an event. A virtual particle is not less real. It is real in a different way, like the wind. You cannot hold it, but you see, the trees bend like gravity. You cannot touch it, but it shapes the path of planets. The virtual particle is the fingerprint of the field, the tremor of the vacuum, the whisper of becoming dot. And in the end, the boundary between real and unreal does not vanish because it was illusory. It vanishes because it was never needed. Reality is not divided into the seen and unseen, the permanent and fleeting. It is a continuum, one where the transient gives rise to the enduring, where the impossible enables the actual, where nothing becomes everything, simply by persisting long enough to matter. So we return to the void, not as emptiness, not as end, but as origin, a sea of fluctuation, a well of potential, a silent engine humming beneath the skin of spinning, and within it, trillions of times each second, across every cubic centimeter of the cosmos. Virtual particles blink into being like stars in a hidden sky, carrying forces, shaping atoms, dreaming up worlds. They are not ghosts, they are the universe, speaking to itself and listening. There is a moment just before dawn, just after the last star fades, when the sky is neither night nor day, a threshold, a breath held between darkness and light. This is where physics now stands, not in certainty, but in liminality, at the edge of understanding, gazing into a realm where particles flicker without existing, where forces act without agents, where cause and effect blur like ink in water. The paradox of virtual particles has led not to resolution, but to revelation that our very concept of reality may be too small. For decades, physicists have wrestled with a quiet crisis. The equations work, the predictions align. The universe behaves as if virtual particles are there, shaping atomic spectra, bending spacetime, seeding galaxies. And yet, no detector has ever captured one. No photograph, no trace, no direct witness. So what are they? Not things, not in the way a stone is a thing, or a photon streaming from a distant quasar. They are symptoms of something deeper, truth buried beneath the language of particles and waves, hidden in the structure of existence itself. And so, from this silence, new visions emerge, elegant, grounded not in observation, but in mathematics so precise it borders on prophecy. In quantum field theory, the foundation of the standard model particles are not tiny billiard balls. They are localized excitations of fields that stretch across the cosmos. The electron field, the electromagnetic field, the Higgs field. These are not abstractions. They are physical entities, as real as the air we breathe, though invisible. A real particle, like an electron detected in a cloud chamber, is a stable ripple in its field, propagating through space, carrying energy and momentum, obeying dung UPRCR加MRC. It is on shell within the bounds of relativity. A virtual particle, by contrast, is an off-shell disturbance, a temporary fluctuation in the same field, sustained only by the uncertainty principle. It does not travel. It does not persist. It connects. It is not an object. It is an interaction. In this view, existence is not binary. It is a spectrum, from fleeting disturbance to enduring excitation. The virtual particle is not unreal. It is less resolved, a whisper in the field's voice. And perhaps that is all any particle ever is, because even the most real electron is never truly isolated. It is surrounded by a cloud of virtual photons. It constantly emits and reabsorbs, altering its effective mass and charge. Strip away the interactions, and the bare particle vanishes into infinite corrections. The mathematical ghost, realization, the process of absorbing these infinities into measurable quantities, reveals a profound truth. Particles do not have properties. They acquire them through relationship. An electron is not defined by itself. It is defined by how it dances with the vacuum. In this framework, existence becomes relational, not a state, but a network. Feynman's path integral formulation deepens this mystery. Instead of a single trajectory, every quantum system explores all possible paths, even those that violate energy conservation, move faster than light, or loop backward in time. Each path contributes a phase, a wave-like amplitude. Most cancel out, but their interference shapes the probability of what we observe. Virtual particles appear in these forbidden paths, mathematical roots that cannot exist classically, yet contribute to the sum. They are not events that happen. They are possibilities that matter, like ripples from stones thrown into a pond that were never actually cast. Their absence still alters the surface, and when measurements occur, the full superposition collapses, not because the impossible paths were fake, but because only some survive interference. Reality, in this view, is a standing wave formed by every conceivable history, and the virtual particle, a shadow cast by a path that never was, yet helped shape what is. Then come the deeper theories, those that seek not to describe, but to REF, RAME. String theory proposes that at the Planck scale, particles are not points, but vibrating filaments of energy strings, oscillating in 10 or 11 dimensions. What we perceive as a virtual photon or electron-positron pair might be transient resonances of strings coupling and decoupling in higher dimensional space. The fluctuations of the vacuum are not random noise, but harmonics of geometry. The quantum foam is not chaos, but music modes of vibration in a cosmic instrument. In this picture, virtual processes are echoes of compactified dimensions, their effects projected into our four-dimensional world like shadows on a cave. Wall.loop quantum gravity offers another vision, one where space-time itself is not smooth, but granular, a fabric woven from spin networks, spracked graphs, whose nodes represent quantized volumes, edges representing surfaces. Here, virtual particles may not be excitations in space, but of space. Their appearance and disappearance could reflect the dynamic rewiring of space-time connectivity, transient links in a causal graph that underlies reality. At this scale, time loses meaning. Events do not unfold. The distinction between past, present, and future dissolves, as in Einstein's block universe. And if time is not fundamental, then causality is not absolute. This opens the door to radical interpretations. Hawking and James. Hartle's no-boundary proposal suggests that the universe has no initial moment to smooth, closed geometry, where time becomes space at the beginning, like the North Pole on a globe. There is no before, no singularity, just a timeless quantum state. In such a model, virtual fluctuations do not begin in time. They define it. The first quantum jitters are not events within space-time. They are the seeds from which space-time grows. And if time emerges, then cause and effect may be approximations, useful for large scales, but irrelevant at the deepest level. Even more provocatively, the transactional interpretation of quantum mechanics developed by John Cramer suggests that quantum events are settled through handshakes across time. When an electron emits a photon, it sends an offer wave forward. The absorber, say, another electron sends a confirmation wave backward. The interaction is completed through a two-way negotiation, with virtual particles acting as messengers in a loop that transcends time. In this view, the future influences the past. Measurement reaches backward, selecting which virtual paths become real. Retrocausality, once dismissed as fantasies, now being tested in delayed choice experiments. In 2017, a team in France demonstrated that a decision made after a photon had already been measured could retroactively determine whether it behaved as a particle or a wave. Outcome depended on a choice made in the future. If such results hold, then virtual processes, being part of the quantum handshake, are not bound by linear time. They exist in a web where influence flows in both directions. And then there is the holographic principle, first suggested by Gerard T. Hooft and developed by Leonard Susskind and Juan Maldacena. It posits that all the information within a volume of space, every particle, every field, every virtual fluctuation, is encoded on its boundary, like a hologram. In the ADS-CFT concrete realization of this idea, gravitational theory, anti-de Sitter space is equivalent to a conformal field theory on its four-dimensional boundary. There is no gravity in the boundary theory, no space-time. Yet, from it, gravity and dimension emerge, and virtual particles in the bulk. They are not independent events. They are projections in Terence patterns in a lower dimensional code. In this framework, the quantum vacuum is not a sea of fluctuations. It is a database, a ledger of correlations. The Casimir effect, the Lamb shift, Hawking radiation, all are computations performed by a universe that stores its secrets on the edge. Reality is not in space. It is of information and the virtual particle, not a physical occurrence, but a subroutine in a cosmic algorithm. Each of these theories speaks a different language. String theory sings in geometry. Loop quantum gravity whispers in networks. The holographic principle computes in bits. But they converge on a single question. What does it mean to be real? We once thought reality meant visibility, tangibility, permanence, but the universe has taught us otherwise. Electrons behave as waves until observed. Quarks are never seen in isolation. Dark matter outweighs visible matter 6-to-1 and yet remains unseen. And virtual particles, they are everywhere, shaping everything, and yet, by definition, unobservable. Perhaps reality is not about being seen. Perhaps it is about being. NECESSARYA, virtual particle, is not real because it appears in a detector. It is real because the universe would collapse without it. Atoms would not form. Light would not scatter. Black holes would not evaporate. The cosmos would lack structure. Its existence is proven not by sight, but by consequence. And in that, it mirrors deeper truths. Consciousness cannot be touched, yet it transforms the world. Love leaves no footprint, yet it alters destiny. Mathematics exists in no physical form, yet it predicts the motion of stars. Some things are real, not because they occupy space, but because they shape it. So we return to the vacuum, not as emptiness, not as void, but as potential, a field, a network, a code, a dream dot, and within it, the virtual particle fleeting, forbidden. Indispensable becomes a symbol of how little we know. of how much we assume, of how fragile our definitions are in the face of a universe that refuses to be named. Because, in the end, the question is not, how can something exist without being real? It is, what if being real was never about permanence at all? What if reality is not a noun, but a verb, not a state of being, but a process of becoming? Then the virtual particle is not an anomaly. It is the purest expression of existence, a flash of connection, a moment of influence, a whisper in the dark, proving that even nothingness knows how to speak. Beneath the Jura Mountains, where time is measured in nanoseconds and energy in teraelectron volts, a machine dreams in code and superconductivity that CERN's Large Hadron Collider. Protons shards of hydrogen-stripped baryons through a ring of copper and niobium, chilled to minus 271.3 degrees Celsius, colder than the void between galaxies. They collide 2,800 times per second, each impact a miniature recreation of the universe's first moments. Detectors, like Atlas and CMS, stand as silent sentinels, recording not particles, but their echoes, energy deposits, ionization trails, fleeting asymmetries in momentum. And within that data, physicists search for ghosts, not literal specters, but anomalies, tiny deviations from the predictions of the standard model. A missing jewel here, an unexpected angle there, a decay rate slightly too fast or too slow. These are the footprints virtual particles might leave if something beyond the known quantum fields were whispering through the vacuum. Because the standard model, for all its precision, is incomplete. It cannot explain dark matter. It does not account for neutrino masses. It fails to incorporate gravity, and it offers no answer to the cosmological constant problem, the staggering mismatch between predicted and observed. Vacuum energy. So scientists look deeper. In 2029, the high luminosity LHC will come online, increasing collision rates by a factor of 10. Billions of events per second will flood petabyte-scale databases, analyzed by algorithms trained to spot the statistically rare quantum loop involving undiscovered virtual particles. Among the most sought after are those linked to supersymmetry hypothetical partners to known particles that could cancel out vacuum energy contributions, solving the cosmological constant puzzle, or virtual heavy neutrinos flickering in loops that generate mass for their lighter counterparts, or even exotic gauge bosons mediating forces between visible matter and dark sectors. Each possibility leaves a faint signature, an imbalance in transverse momentum, a resonance at an unexplained energy, a decayed branching ratio askew. The hunt is not for a flash of light, but for a tremor in probability. Above Earth, another kind of silence is being studied. Launched in 2023, the European Space Agency's Euclid telescope drifts at the Sun-Earth L 2.1 million miles from home. Its mission: to map the shapes and positions of 2 billion galaxies across 6 years, charting the cosmic web in unprecedented detail. But Euclid is not merely observing structure. It is measuring time by analyzing how galaxy clustering evolves across redshift. Euclid tests whether dark energy, the dominant component of the vacuum, remains constant or changes with cosmic expansion. If the energy density of empty space shifts, it could mean that virtual particle contributions are not static, that the quantum foam itself stretches and breathes with the universe. Such a discovery would shatter the assumption of a fixed cosmological constant. It would suggest that the vacuum is dynamic, responsive, living medium rather than a rigid backdrop, and if so, then virtual processes may have varied over cosmic history, altering the strength of forces, the stability of atoms, even the rate of inflation. Further into the infrared, NASA prepares a space observatory set to launch in 2025. It will scan the entire sky in 97 spectral bands, searching for subtle distortions in the cosmic microwave background, CMB, the afterglow of the Big Bang, among its targets. Primordial non-Gaussianized deviations from perfect randomness in the temperature fluctuations of the early universe. Such patterns could be fingerprints of complex inflationary dynamics where multiple quantum fields interacted, producing virtual fluctuations beyond simple single-field models. If detected, these imprints would reveal not just that quantum jitters seeded galaxies, but how, whether they arose from a single inflattened field or from entangled networks of virtual interactions, possibly involving extra dimensions or stringy resonances. These are not searches for objects. They are inquiries into origin. Meanwhile, deep underground, where cosmic rays cannot reach, another kind of listening takes place at the University of Washington and Fermilab. The Axion Dark Matter Experiment, a DMX, operates inside a powerful magnetic field, cooled to near absolute zero. It waits not for collisions, but for whispers. Ixions are hypothetical particles proposed to solve a symmetry puzzle in quantum chromodynamics, but they also happen to be excellent dark matter candidates, and crucially, they could emerge from the vacuum as virtual entities before becoming real, stable constituents of the cosmos. ADMX attempts to convert them into detectable microwaves using the Primakov effections exist. They should occasionally materialize as photons in the presence of a strong magnetic field. It is a search for matter born from nothing, for particles that began as fluctuations and never vanished elsewhere. In quantum optics laboratories at MIT, Caltech, and the University of Constance, scientists do not wait for nature to reveal its secrets. They recreate them using superconducting qubits and ultra-fast lasers. They manipulate the quantum vacuum, directly engineering squeezed states where uncertainty is redistributed, reducing noise in one variable while amplifying it in another. In these controlled vacuums, fluctuations can be enhanced or suppressed, allowing researchers to probe the churning substrate of spacetime with unprecedented sensitivity. Squeezed light has already improved gravitational wave detection at LIGO. Now, it is being used to visualize vacuum fluctuations, themselves mapping the invisible jitter that underlies reality. Even more daring are experiments simulating black hole event horizons. In Bose-Einstein condensates, researchers create analog horizons regions where waves cannot escape, mimicking the trapping of light by gravity. At these boundaries, phonons, or photons, separate in pairs, one trapped, one radiated. Hawking radiation in miniature. Jeff Steinhauer's team in Israel has observed thermal spectra and quantum entanglement between these analog pairs of evidence. that virtual fluctuations can indeed be torn apart by horizon-like conditions, converting the unreal into the real. These are not black holes, but they are mirrors, distorted reflections of quantum gravity in tabletop systems, and they suggest that if we can simulate the birth of real particles from virtual ones, we may one day control the boundary between existence and potential. On larger scales, computational physics advances in parallel. Using lattice quantum field theory, supercomputers model space-time as a discrete grid, simulating how quantum fields evolve under extreme conditions. These simulations reveal how virtual interactions give rise to emergent phenomena, confinement of quarks, phase transitions in the early universe, even hints of geometric structure arising from entanglement. Some models suggest that space-time itself may condense from a network of virtual exchanges, a foam of causality, where locality is not fundamental. But derived in this view, the smooth continuum Einstein described is an illusion, like the surface of water appearing solid from afar. Up close, it is turbulence, conductivity, fluctuation, and at the center of this inquiry stands the Event Horizon Telescope. Since capturing the first image of M87 in 2019 and Sagittarius A in 2022, the EHT collaboration has refined its global array of radio telescopes, achieving resolutions fine enough to probe the immediate vicinity of black hole shadows. Now, they search for signs of a quantum atmosphere, a halo of intense vacuum fluctuations just outside the event horizon, where virtual particle production reaches extremes. Some theories predict this region could emit faint, coherent radiation or alter photon polarization in detectable ways. If such signals appear, they would be the first direct observational evidence of quantum effects dominating space-time geometry of virtual processes, shaping the edge of oblivion across continents and disciplines. The pursuit continues, not for a single answer, but for coherence, from subterranean axion hunters to orbital telescopes scanning ancient light, from squeezed vacuum chambers to simulated black holes. Science converges on a singular mystery. What is the true nature of the unreal? Not as fantasy, not as fiction, but as foundation. Because every experiment, every observation, every line of code reinforces one unsettling truth. The universe does not run on what we see. It runs on what we cannot, on disturbances in fields, on paths that cancel, on information encoded on horizons, on particles that exist only to vanish and, yet without which nothing would remain. And perhaps the greatest revelation is not that virtual particles are real in some hidden way, but that reality itself may be virtual, a projection, an approximation, a stable interference pattern in an ocean of possibility. We speak of discovery as if it means finding something new, but maybe discovery is remembering what was always there, hidden in plain sight, buried in equations, written in the silence between measurements. The vacuum hums, the fields fluctuate, the universe listens, and somewhere, in the space between cause and effect, in the gap between detection and denial, the unseen architects continue their work building reality, one ghostly exchange at a time. There is a moment rare, quiet, when the mind lets go of certainty, not ignorance, not confusion, but surrender. a recognition that the universe does not owe us solidity, that permanence may be the dream, and impermanence the truth. We stand now at that threshold, not at the edge of space, nor at the beginning of time, but at the boundary of understanding, where equations speak in riddles, where detectors record absences, where the most powerful force in existence is not gravity nor energy, but influence without presence. For decades, humanity has searched for the building blocks of reality. Leptons, bosons, each discovery celebrated as a conquest over mystery. And yet, beneath them all, something else persists. Something that cannot be held, cannot be seen, cannot even be said to exist in any classical sense. And still, it governs. The virtual particle fleeting, forbidden, unobservable shapes atoms, bends light, mediates forces, seeds galaxies. It emerges from nothing, lives less than a trillionth of a second, vanishes before it can be caught, and yet without it the cosmos would unravel. It does not shine like a star, it does not crash like a wave. It whispers, and the universe listens. From this silence arises a new vision of what is real, not substance, not matter, not even energy, but relationship. An electron is not defined by its mass or charge alone. It is defined by how it exchanges virtual photons with other particles. A proton's stability depends on gluons flickering between quarks, ghostly messengers holding it together. Even mass itself, the very resistance we feel when pushing against the world, comes not from internal substance, but from interaction with the Higgs field, mediated by virtual Higgs bosons. What we call a particle may be nothing more than a knot of sustained connection or resonance in an endless network of exchange. And if so, then perhaps being is not a state of enduring, but of touching. Like two voices harmonizing across a canyon, one brief note altering the shape of another, gone in an instant, unrepeatable, yet the air still trembles. Einstein taught us that space bends, that time slows, that the fabric of reality is fluid, responsive, shaped by what moves through it. Hawking revealed that black holes are not eternal prisons, but radiating bodies slowly dissolving into the vacuum, their fate sealed by virtual pairs torn apart at the event horizon. Quantum theory goes further. It suggests that nothingness is not empty, that the void breathes, that the vacuum pulses with potential, so alive that entire universes might emerge from its fluctuations. And in that revelation lies both wonder and humility, because if the foundation of all things is not rock, but ripple, if the engine of existence runs on borrowed energy and fleeting possibility, then everything we know is balanced on the edge of disappearance. Atoms, stars, life, all temporary configurations of fields, all sustained by exchanges too brief to measure, all destined to fade. Even the cosmos itself may be no more permanent than a virtual fluctuation born from a quantum jolt in a prior void, expanding, cooling, forming galaxies and minds that ask, why are we here? And one day, perhaps, returning to silence in this light, the distinction between real and unreal collapses, not because science has failed, but because reality was never what we thought. We built our philosophy on permanence, on objects, on nouns, but the universe speaks in verbs, in interactions, in transitions. A virtual particle does not exist first hit happens. An event, not an entity. A handshake between fields. A transaction across spectrum. And perhaps we are the same. Consciousness does not reside in a single neuron. Love is not stored in a heartbeat. Memory is not fixed in the brain. They are patterns, processes, resonances in a vast biological network, emergent, transient, meaningful only in relation. Like virtual particles, we appear, we interact, we influence, then we vanish. Our thoughts echo in others. Our actions ripple through time. Our civilizations rise like fluctuations in the social vacuum, brief peaks of order in an entropic sea. Do they last? No, but do they matter? Yes, because meaning may not lie in endurance, but in impact, just as the lamb-shifted deviation, smaller than a whisper, confirmed the existence of virtual particles. So too can the smallest act alter the course of a life. A word, a glance, a decision made in darkness. The universe does not reward permanence, it rewards connection. And in that, there is beauty, not the beauty of monuments, carved to resist time, but the beauty of fireflies in the night, fleeting, fragile, glowing just long enough to be seen, or of waves meeting on the shore, colliding, rising, dissolving, each unique, each gone, each necessary to the motion of the sea. To accept the virtual is to accept transience. Sacred it is to understand that something can change. The universe without ever being. Real in the way a stone is real. A photon from a distant galaxy travels for 10 billion years before striking your eye. In that moment, you see the past. You touch deep time, but the photon vanishes, absorbed, converted, gone. Was it less real because it ceased to exist? No, it was real because it arrived. Likewise, the virtual particle is real because it acts, because it shifts an energy level, because it pushes two plates together, because it allows a black hole to evaporate, because without it, none of this would be. So perhaps the deepest mystery is not how something can come from nothing, but how nothing can do so much. And in that paradox, we find a mirror. We, too, are brief. We, too, are made of fields dancing in spatial with. Too will vanish. But while we are here, while the resonance holds, we touch the world. We alter probabilities. We become part of the interference pattern of existence. Maybe that is enough. Maybe it is everything. For if even the unreal can shape stars, then maybe love, though it leaves no fossil, is written in the structure of Spetnup. Maybe grief, though it cannot be weighed, bends the vacuum like mass. Maybe hope, though it flickers, is a fluctuation that refuses to cancel out. The universe thrives on impermanence, on the constant churn of becoming and unbecoming. On the courage of things that dare to exist, knowing they will not last. And so, in the end, we return to the void, not as emptiness, not as end, but as source, as field, as home, and within it, across every cubic centimeter of space, trillions of times each second, virtual particles blink into being like stars in a hidden sky, carrying forces, shaping atoms, dreaming up worlds they do not endure. They do not demand witness, they simply are, briefly, between one state and the next, and in that instant, they change everything.